For this video, I am going to show the proof of theorem an edge E of a graph G is a cut edge of G if and only if it is not contained in any cycle of G. Before we will proceed to the proof, let us review first on the definition of path and cycle. A path is a walk that does not include any vertex twice, except that its first vertex might be the same as its last. Example, we have this graph. The path v, w, x, y, z is an example of a path in this graph. Now observe that in this path, we did not use any of the vertices. We did not use any of the vertices more than once. However, in the cycle, since it is a path that begins and ends on the same vertex, hence we can use one of the vertices in the path. We can use it more than once. For example, we have v, w, x, y, z, v. So we go back to the starting vertex. So we started at v and we ended at v. Okay, so this is the theorem. Now in the theorem, it is in an if and only if statement. That is why we have to show two proofs. The first one is that we have to show that if E is a cut edge, then it is part of no cycle. Number two, if E is part of no cycle, then it is a cut edge. So we have to show first the first one. If E is a cut edge, then it is part of no cycle. So based from the given condition, if E is a cut edge, okay. So if you can still remember, we have discussed what is a cut edge in our previous video. So if E here is a cut edge, then removing E from this graph will result to a disconnected graph. Okay, so let's start. So here is the proof. So let E, which is UV, so this is our E, UV. We can also name our edge, instead of E, we can also name it as UV. So we are using the two endpoints or the two vertices that E is incident to. Okay, so let E be a cut edge of G. Then the vertices U and V must be in different components of G minus E. Then if E is a cut edge, then the vertices U and V must be in different components of G minus E. So again, based from the definition of a cut edge, if E is a cut edge, then U, if we're going to remove E, again, based from the definition of a cut edge, G minus E, removing E from this graph, G, will result to a disconnected graph. Okay, it will result to a disconnected graph. So let's remove. Okay, so let's try to remove this one. Okay, so when we remove the E, what happens now is that U and V is in two different components. This is one component and this is another component. So this is our G minus E. Okay, that is our G minus E. Okay, so this is the continuation of the proof. So in here, so the first part of the proof is that we showed that what will happen what will happen if E is a cut edge. So when E is a cut edge, in this particular illustration or in this particular graph, if E is a cut edge, then U and V belongs to the two different components of the graph. Okay, so that was the first part of the proof. Now, for this part, we cannot show it by using a direct proof. Instead, or I mean, it's much easier if we are going to use, um, if we're going to show the proof by using a contradiction. Okay, so it says here that E should not be part of no cycle. So E, the edge E, should not be a part of any cycle in G. So to contradict that, so let's say E contained in cycle C in G. Okay, let E, this one, let the edge contain in a cycle G, in a cycle in G. Okay, so let us see some of the, let us show that there is a cycle in G. Okay, so let's say this is the vertex. Okay, so we'll have a path from here, here, so let's say here, there, and there. Oops, I cannot go to U. I cannot go to vertex U. Because again, by definition of a path, we can only use the vertex once, but unless we will go back to the starting vertex. Okay, whatever vertex that we used as a starting point for our path, for our walk, then we should end there. Okay, we should end there. So in this case, I cannot go to U and then go to V, and so that I can go here, okay, to the vertex where we started. So let's say I have here an imaginary edge. Okay, so let's say, for example, this is our graph. There is an imaginary edge here. Okay, so in this case, we can say that there is a cycle in this graph. There is a cycle in this graph, and that E is part of the cycle. Okay, it's part of a cycle. Now, then C minus E is a path between U and V in G minus E. It means that if E is truly a part of a cycle, removing E from the cycle, okay, removing E in the cycle, so that is C minus E. Okay, removing E from the cycle, still there is a path, there will still an existing path that will connect U and V. So this is the existing path that will connect U and V. That is, if E, the edge E, is truly a part of the cycle. Again, if E is truly a part of the cycle C in the graph G, then removing E from the graph, which is ito na nga, we denoted C minus E. When we remove E, we denote whatever the resulting graph is as C minus E. So when we remove E, still there is a path connecting U to V. However, However, when we say C minus E, that will also result as 2G minus E. Okay, G minus E. Again, when we removed E from the cycle, which is C minus E, that is the same as G minus E. Because this is the entire graph. This is G, right? G. So G minus E. However, we have discussed at the beginning of the proof that in G minus E, U and the vertex U and V are in a different components, in two different components. Okay? They are in two different components. And when we say that U and V are in two different components, meaning there is no connection between the two components. Okay? There is no path. There is no path between U and V. That is why we can say that E is not part of any cycle in G. Now let us show the proof that if E is part of no cycle, then E is a cut edge. Now in here, we have to show, okay, this is based from the definition of a cut edge. We have to show here that if E is a cut edge, then G minus E is disconnected. Again, for us to show that E is a cut edge of this graph, then G minus E is disconnected, which means U and V are in different components. Okay? So let us assume that E is not in any cycle of G. So this is our assumption. E is not part of any cycle in G. Okay, so if E is not part of any cycle in G, then there is no UV path other than E. We have shown in the first proof that if E is in any cycle, then when we remove E, still there is a path connecting U to V. Okay? Again, if E is part of a cycle, so let's say we have this one, this imaginary edge. So this is our cycle, no? This is our cycle. Okay, this is our cycle. Now, if E is part of the cycle, then removing E, when we remove E, still there is a path from U. So this is the path from U to V. So that's the path, no? If E is part of a cycle. However, if E is not part of the cycle, okay, if E is not part of the cycle, the only way for U and V to be connected is through E only. Through E only. There's no other path, there's no other edges that can connect U to V. Okay? So then there is no UV path other than E. Therefore, U and V are in different components of G minus E. So when we remove E, when we remove E, there's no other path, okay? There's no other, there are no other edges that can connect U to V. Therefore, we can say that U and V are in different components of G minus E. And that since U and V are in different components based from the definition of a disconnected graph, G G minus E is a disconnected graph. Okay. The definition for a disconnected graph is that the graph has different components, at least two different components. So since U and V can be found in different components, in this case, we can find U and V in two different components of G minus E. Therefore, we can say that G minus E is disconnected. And again, by definition of a cut edge, therefore, E is a cut edge.